students, if you are hearing me, let's consider case number one. Case number one, because the basic definition of torque you already know, force into perpendicular distance. I'm not going to bore you with that. Okay, so case number one, let's consider the magnetic field, students, to be inside. Okay, inside the plane. And please pay attention. There will be some concepts here where visualizing or imagining certain things might be difficult, so I will try my level best. Okay. So if the magnetic field, students, B is inside the plane and I am putting a coil here, this is a coil. We won't call this a loop now. So this is a coil, okay, and it is having a current in the direction I, students. It's having a direction I, like this. In that case, students, can you tell me where is the force going to be at for each branch? For each branch, what will be the forces? Will it be opposite and equal in magnitude?
Yes, sir.
It will be opposite and equal in magnitude. So of course you can apply your right hand rule for this line here. Right hand rule, right side you will get force. Okay, because this is dl. For this over here, dl will be upward, students. So dl cross b, you can apply dl cross b. Your force is over here now. Similarly, for this, if you apply dl cross b, you will get the force to be downwards too. And for this also, you will get a force upwards. So students, listen to me. Listen to me. Here, can I say that the forces basically, in this case, are all cancelling off each other? They are all cancelling off each other. Yes or no? So I can say that the force on the loop is basically 0. Force on the loop is basically equal to 0, students. But what is the torque? Will the torque also be equal to 0? Can the torque also be equal to 0?
No, sir.
Why? Why is that? Why do you think like that? Any reason? Specific reason? Okay, so that was a guess. Fine. Any other one? Any other person who has a specific? Who has a specific?
Sir, maybe
reason?
the dl
Okay.
vector is in
Yes.
the same direction. That's why.
dl vector is in the same direction. Okay. So
In
students,
the
the best.
clockwise.
Right. I get it. Yeah, you're saying dl vector is clockwise, so maybe it has some torque. That's what you're saying. Okay. Best way to do it is apply a concept of engineering here. Okay. This concept I will tell you is to basically visualize this thing, this entire thing, in the most simplistic way. Okay. We will not now. We are trying to look at this from your perspective. Your perspective is basically magnetic field is going inside, but I don't want to see it that. To make things easier for me, let's consider this one person is here. Okay, right? This person is you right now, and this person goes on top and looks down. Then how will this look? Okay, that is the main thing. That is the main thing. So let's try to visualize that. Okay, I will draw the same diagram, and you will see how we can basically visualize this entire thing in different perspectives. Okay, so students, please pay attention. This is about perspective. Okay, so I am saying that this magnetic field is basically like this, right? I said the magnetic field is like this, and I am saying that there was a loop here. This was my loop. It is having some current and it is in the clockwise direction. Let's say it's in clockwise direction. But if I consider the same thing downwards, now students, look here. For example, how do I say it? Let's talk about a cube. Okay, cube. Let's say cube. Let's do it like this. Look here. Look here. Everyone look here. Okay. So this front surface number 1. Okay, the surface number 1 is where my loop is. Yes or no? Surface number 1. This is where my loop is. Front surface. Yes or no? Front surface.
Yes,
but my magnetic field is inside the plane. Means what? It is going like this. My magnetic field is going inside the cube like this. It is having some direction like this. Yes or no? So if I look at it from a top perspective, can I see my magnetic field lines basically going in some certain direction like this? And from the top perspective, students, okay, this coil here, this coil which is placed here, okay, from top will look like a line, no? You will only see this line. Are you understanding? Are you understanding, students? From the top,
Yes,
from
sir.
the top, from the top, students, magnetic field lines are basically going inside the cube like this, inside. So from the top, you will see something like this. Okay. Second point I'm saying is the same loop, basically, which is actually a wire only. It's a strip of a wire. Okay. I have placed it here on surface number one. Here, top, front. Okay. So from the top, you will see only one line like this. You will see one line. How you will see it? You will see it like this. You will see it like this, right? Now what? Now remove your attention from here. This is a different perspective, students. This is how you can imagine perspectives with respect to a cube. Why? Because cube is only the shape which is having an x, y, and a z axis in symmetrical. Of course, there are many shapes, but this is the basic shape. X, Y, Z. It gives you a different perspective. You can look at the cube from any angle. If you look at it from here, it gives you a different perspective. From here, different perspective, and so on and so forth. Okay, we won't waste time on that. But students, now the thing is, we're going to ramp our sums up. Look here. Uh, when you look at this from a different perspective, this entire thing looks like this. Okay, magnetic field, basically, magnetic field is going in this direction, students. Okay, and your loop is basically from the top a line, just looks like a line. So students, look here. In this loop here, current is in what direction? Clockwise direction. Can I say that? Current is in clockwise direction. But when you're looking at it from the top, students, even though this is in clockwise direction, students, okay, from the top, at this point, is the current coming towards this man? Is the current coming towards this man? Yes. So I can say the current is
Yes, sir.
coming out. I can say the current is coming outwards. And towards this man, which is here, current is moving downwards because it's clockwise. You can understand this? Everyone can understand? Can everyone
Yes,
tell me
sir.
a yes or no? Only one
Yes,
person
sir.
is telling.
Yes, sir.
Yes, sir.
Okay, all of you. If anywhere you all are getting interrupted, please let me know. This is important. Magnetic field, I won't be explaining perspectives. It becomes tough. Okay, so look here. From this perspective of this man, you can see a line of the loop. Fine. Okay. Now, second thing I told you is the current direction is clockwise. So from this perspective, from this man's perspective, current at this point is basically coming outwards and current over here is going downwards. So I can say the current here is going downwards. Inside. Current is coming outwards, current is going downwards. Second thing we saw just as we started the lecture is the forces by applying right hand rule. One is coming here, another force comes here, yes or no? Another force is here, and one more force is here. So in that case, students, in that case, from the top, what are the two forces I will be able to see? Can I say it is going to be this side and this side? Yes or no?
Yes, sir.
Two horizontal. That means force is over
Yes,
here.
sir.
One force is over here, and one force is over here. Why I taught you so much? Why I taught you so much? Okay, forget this entire thing now. This entire thing is of no use for us. That is only to understand perspective. Okay, if at all doubt is there, let me know. We'll finish it as fast as possible. See, force from the top, Okay, that is now you are on the top. That cube was there, the person was there. That person is you now. You look at this entire loop in which current is coming outwards here, current goes inside here, and the force here from the top. Okay, you will not look at these forces. You will basically look at these forces. These forces come into picture. So students, look here. Torque is basically what? Force into perpendicular distance. Perpendicular distance. But perpendicular distance to what, students? To the force. Is there any perpendicular distance to the force here? Is there a can you see a perpendicular distance anywhere?
No,
With
sir.
respect to, you can't. Similarly here, there is no perpendicular distance. There is no distance like this here. There is no perpendicular distance between the force. So here, perpendicular distance and force are basically not, force might be there. Okay. But they're cancelling off each other here, right? Another way to see it is, there is no perpendicular distance with respect to force. Why? For example, we are talking about a car, students. In a car, there is a wheel. Okay. And if this is going to be a point at which I want to remove the torque will be force of this. Say, suppose this is having a force in this perspective, force here. Then perpendicular distance is basically this. Yes or no, students? This becomes my perpendicular distance. Force into perpendicular distance will give me some torque. But students, here there is no perpendicular distance at all with respect to force. So I can say that force in a loop is anyway zero. Force in a loop is anyway zero, and torque also is going to be zero. But this is case one, students. What is case one? Case one is when you are taking this case one, students. Look here. Okay, everyone. The loop over here is at what angle with respect to the, is at what angle with the magnetic field, students? Is at what angle? Theta is equal to what? Theta between the loop and the magnetic field. What is it?
90 degree.
It's 90
90
degrees. No?
degree.
Yes or no? Force is equal to what? I dl cross B. I dl cross B. And so dl and B. Okay. I dl B sine theta. Right. So sine 90 is what? Sine 90 is going to be. Okay. So you understand. You get the fact. The torque is also going to be equal to 0. Force is also going to be 0. But this is case number 1. Case number 1 is basically when your loop, when your current loop is kept at exactly 90 degrees with the magnetic field. Okay. Has everyone understood this?
Yes, sir.
All of
Yes,
you?
sir.
Okay. So without wasting much time, students, let's go to case number 2. And this is where a little bit of uh, imagination is required, little bit of perspective. Okay, so let's say that my magnetic field, students, is again inside. It's inside. Usually in this chapter we always take our magnetic field to be inside for simplicity. So this is our magnetic field, students, and this time let's say that the original position of my loop was how? 90 degree, right? It was 90 degree. It was like this. But now I say I'm going to twist it, students. I'm going to twist it. So let's say that I twisted this with the some angle theta. I twisted it by some angle theta, right? Can you see that angle? Is that going to be okay? I can say that this is theta, right? Let me draw that again because so you can clearly see that there are two positions here. One is case number 1 and one is case number 2. Case number 2 is when I take this loop black color and I twist it at some angle theta. At some angle theta. So then what happens to it? Then what happens? So we already know one thing. We already know one thing, that force in a loop is what, students? Force in a loop is anyways going to be 0.
0.
You all know this. Yeah. Okay. But what about torque, students? Torque will be what? What is the torque? So when we talk about force in a loop, students, it's the net force. Huh? It's the force because all at all branches they're equal and opposite. Because okay, all branches forces are equal and opposite, cancelling off each other. Net force in a loop is going to be 0. Fine. I'm not going to manipulate that. Okay. Otherwise you will get confused. Let's look at the same thing, students. Let's look at the same thing from a different perspective, right? Just like we did the earlier thing. Okay. So I said that there is going to be, I do this so that you understand this quite well, that there is a cube, students, and in this cube, this time the surface number 1, okay, forget the surface number 1, I'll draw another I'll draw a loop here, and this loop is basically placed like this. Huh? It is placed like this. Look here, along this, and it is like this. You can see that. Can you see it how I placed it? Can you see it how I placed it? It is at a certain, it is not surface number 1 now. This is theta, students. Okay, this is theta. Don't worry about it. Just try to understand something. So right now we are looking at it from where? From the front perspective. From the perspective, from this, we are looking. The person is you right now. You are looking through this surface, through the entry surface. But let's shift our perspective. Let's say the man is here. Let's say we are here. From here, students, from here, okay, how is this going to look? From top, how is it going to look? So we can understand that if magnetic field is inside the plane, basically my magnetic field is going like this, isn't it? My magnetic field is going like this. Yes or no, students? You can imagine that? Is that yeah, it's going inside,
sure.
students. Yeah, it's going inside. See, it's all going inside. Magnetic field, all is going inside the cube. So from the top perspective, this man can see that the magnetic field is basically in this direction. He can only see this. And students, if he is seeing this, from the top he is only seeing a line of the loop. And that line of the loop is basically slanted. It is slanted. So I can say that this is also going to be slanted. Can I say this is my top view, students? Any problem here?
No, sir.
Okay. So there should not be any problem, students. So look here now. Look here. I'm going to rub all of this because till now no one has told me that they have any doubt. Otherwise, if I keep explaining perspectives, we won't be able to cover it up. Okay. So look here. Students, I'm going to draw that very thing and we are going to derive something beautiful. Look here. So this is the top perspective, students. This is our top perspective. And the loop is basically like this. Okay. Now, students, when I told you, just a second, give me a second. Yeah, okay. So when I took a loop, students, like this, when I had taken a loop like this, and the current was like this, right? It was in, I'm saying it was in clockwise direction. So now you only tell me from the top perspective, okay, from the top perspective here, if the man was here, the current is coming outwards, yes or no? Current through this branch is
Yes,
coming
sir.
outwards towards him. So I can draw that the current basically is coming outwards. I will draw vector form over there. And similarly over here, I can see that the current is going downwards. Don't get confused when I said vector form. It's just a representation of current coming out or down. So now here it is going downwards, students. Can you see that person is basically looking at the current going down at this perspective? Fine. So this is a major thing which you have to understand. After this, everything becomes simple. Now, let's consider the loop. Okay, each side of the loop is having some length L. So I will say this length is going to be L. In that case, students, in that case, if I have to say that I want to find out the length at the center, I just have to do what? How much is the length going to be from the center, students?
L by 2 sin theta.
It's going to be L by 2. It's going to be L by 2. Okay. This length and this length will be L by 2. This entire thing is L. Now, students, let's try to find out the direction of the force here. Let's try to find out the direction of the force. Look at this here. Okay, this. Students, if the current is coming out, is my DL also coming out? Is my length vector also coming out? Can I say my length vector is coming out?
Yes,
Yes
sir.
or no? So if this is my magnetic field, students, if B is my magnetic field and DL is coming out, what is DL cross B? In which direction will I get my force, students? DL is towards you, like this. And magnetic field is, are you getting the thing? DL is coming towards you. Magnetic field is upwards. So what is DL cross B? In which direction? Left, right, up or down?
Left.
I want
Left.
the answer. I want the answer from at least 4 or 5 people. Please tell me where is going to be left? Yeah. Hope you all are getting it. Or you can simply look at this like this. It was simply clockwise here, right? It was simply clockwise here, and our magnetic field was basically inside the plane here. So DL cross B will give me a DL cross. Okay, DL cross B. Sorry, will give me a force upwards. Here it will give me downwards. Here rightwards and here a left. So you can see from the top, this man can see the direction at this point to be right, and at this point to be left. Yes or no? Easy? Is that easy? Okay, so here
Yes, sir.
current, for those who are not understanding, here current is coming towards you. So my length vector also will come towards you. In that case, students, length vector, keep your 4 fingers towards the length vector and curl the 4 fingers towards D, magnetic field. In that you can see that your thumb points towards the left side. So your force will be on the left side. Similarly over here, dl vector is basically inside, students, and magnetic field is going outwards, inside. So in that case, my force is like this towards the right side. That should not be a confusion. Now students, we know that F is equal to what? F is equal to I dl cross B. Yes or no? I dl cross B. But what is, if I open this up, students, I will get dl B sine theta. Yes or no? What is theta over here? What is theta over here? I'm talking only for these forces. Huh? These forces. Just for this line, students, this line here. And this line. Magnetic field is inside only, na?
90 degree.
90 degree. Everyone understood this? Here it gets a little bit confusing. Students, listen here. Magnetic field is inside only. I'm not asking you what the loop is making with the magnetic field. Loop is making some angle theta, that I understood. But what about this branch? Is this branch going to have any angle? DL vector is where over here? DL vector for this branch is upward, students. DL vector for this is what? Downwards. This length vector and the magnetic field, are they making any angle, students? It is going to be 90 degree. Can you agree with me on that? Yes, no? Difficult to understand?
Yes, sir.
No? I'm not getting a confident yes. Why am I not getting a confident yes? Look here. I just told you that the magnetic field initially was like this. And now I am just telling you that there is a loop. Okay. I'm telling you there is a loop. This loop has been turned by some angle theta. Fine, I know it is some angle theta here. Okay, no problem. But if I look at the current direction is how we are. It was like this. And if I'm only talking about this line, my dl vector will be along the current. So this becomes my dl. So you can see magnetic field is inside, students. dl is upwards. So dl and magnetic field is going to make 90 degree. Similarly, over here, students, I'm just talking about this branch here. This branch. This branch also will make a 90 degree with the magnetic field. Yes or no? dl vector. This dl also will make a 90 degree with the magnetic field. So I can say that my force on this branch, okay, my force on this branch, which is coming out towards here using right hand rule, will be what? I L B sine 90 is what? Sine pi by 2 is 1. So I can say I L B. Yes or no? So my force here will have a magnitude I L B. And the force here also will be having a magnitude I L B. Clear, everyone? Clear?
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
Yeah. So if my force, students, now comes the important part. Look here. Now, definitely we know that torque, students, is equal to force into perpendicular distance. Now can you see, students, is there a don't tell me what is the value of it. Is there a perpendicular distance with respect to the force? Can we say yes? Can we say yes? Isn't it? So because this is the length, I can find out the perpendicular distance with respect to the force. Yes or no? So what is going to be what is the perpendicular distance going to be? I said that the loop was making an angle. The entire loop was making an angle. How much it was making an angle? Theta. It was making an angle theta, isn't it? And this length is what? L by 2. This length is also L by 2, considering the fact that the entire length here, students, is L. Entire length is L. So half of its length from the center is L by 2. And L by 2 cos theta will give me what? L by 2 cos theta will give me what, students? It will give me the length in the x-axis direction. Yes or no? You can see. Yes or no? Look here. If this is L, this entire thing is L. Of course, this is L by 2. And this is also L by 2. In that case, if this is my x-axis and this is my y-axis, this loop here, this is the loop from the top direction, is making an angle theta. In that case, on the x-axis, I will get L by 2 cos theta. On the y-axis, I get L by 2 sin theta. And L by 2 sin theta, which is going to be the perpendicular distance, it will be a perpendicular distance with respect to the force. Yes or no? It will be perpendicular
Yes.
distance with respect to force. So in that case, students, we can say that the force, torque, which is equal to force into perpendicular distance. Here the force is what? ILB into perpendicular distance, students. Perpendicular distance will be what? L by 2 sin theta. But there is a catch here, students. Here we are considering only one force. But how many forces are there, students, on this entire loop? 2 is there, which is causing the torque. 2 forces are there. So instead of writing ILB, I will write torque is basically equal to 2 times ILB into L by 2 sin theta. In that case, students, 2 and 2 gets cancelled. L gets multiplied, B sin theta. So it's going to be what? L square B sin theta. L square B sin theta. Okay. Is that understood? So torque basically is going to be equal to L square B sin theta. But here comes another catch. L square is what, students? In a square, if I have to tell you to find out the area, length into length is basically what? Area.
Area.
Can I say that L square is area? Area of what, students? Here now this is where we get into another concept. Okay, this is a torque, students. L square B, but now I will write area into B sin theta. Torque now, students, turns out to be in the form of area also. It comes in with the parameters of area, magnetic field, everything, sin theta. But if I rearrange this term, students, I can say that it is going to be equal to IA cross B. Can I say that? IA cross B, where area also can be defined as a vector, magnetic field also can be defined as a vector. Area also can be defined as a vector, and magnetic field also can be defined as a vector. Okay. So, for all those who have understood, can you write in your chat that you have understood? All of you all, just write yes. So at least I'll know how many have understood. That would be a great help. There is absolutely no doubt, right? There's absolutely no doubt. Great. Okay. Wow. I thought I'll have to do a lot of I thought I'd have to do a lot of perspective. Okay, great. All of you all have understood. Yeah, that's great. Good answers. Okay. So if that is understood, students, then ultimately I'm saying that my torque, there is going to be a torque. Okay, there is going to be a torque here, and that is just because I have shifted it by a certain theta. Torque comes out to be what it comes out to be. Now, do you all remember? It is L square cross B, which is basically IA cross B. Okay, this is where I will introduce to you something called area vector. Of course, we know what is area vector. I'm going to rub this off, students, now. Rub this off. And here we come to a concept called area vector. So now this becomes a shortcut for us to understand torque. Okay, so please pay attention. There's hardly any time, but no problem. You can understand at least some concepts here. That if my loop, students, if the current loop is having some direction current I, if it is having some direction current I like this, and it is in clockwise or anti-clockwise direction, you don't need to find out what is going to be the length, then find out what is going to be the magnetic field, then multiply them, cross product, then find out the torque. No, all that not required. All you have to do first, if in case you have a loop, first assign the current if there is no current. Then you can also assign the direction of area vector. And area vector can be assigned by using a right hand thumb rule. Look here. The current is going to be in clockwise. Take your right hand, apply it across the entire loop. Apply it across the entire loop. In that case, students, area vector here in this case is going inside the plane. Is going inside the plane. Let's look at another example here. That if suppose my loop was there, it again had an angle theta. This time it is going to be anti-clockwise, students. This time it is going to be anti-clockwise. In that case, just apply your right hand rule and curl your fingers across the current. Curl your fingers. So whenever you have a coil, first concept, take your fingers, curl it around the current direction, and that your thumb, and in that case your thumb will be exactly pointing towards the direction of the area vector. It will be pointing out towards the direction of the area vector. Now, of course, I can't draw this outside the board, so you can get an idea that it is basically coming out. And so it becomes easy, therefore, to find out the direction of the area vector. Okay, this is one important thing. It becomes easy. Direction can be found out by curling your fingers in the direction of the current, and thumb will give you the direction of the area vector. In that case, IA cross B, it is very easy to find out just by, of course, you can find out the area, magnetic field, but direction is also important, students. So in that case, you know what the area vector's direction is also, and same thing, torque will also be in that same direction. Torque will also be in the same direction. So that is why we are looking at the area vector. Okay, so how do we find out the direction of the torque? Basically, torque will be parallel to area vector A cross B. Okay, torque's direction of the torque will be basically in the direction of A cross B. For example, if I have to say that my magnetic field, students, how much time we got? We got 5 minutes, right? So if my magnetic field, students, was inside the plane here, okay, if it was inside, students, and I have basically told you that my there's a loop here, and this loop is having some angle theta, and there is a current I here, and it is going clockwise. Okay, it's going clockwise. Now let's take it anti-clockwise. Let's say it's anti-clockwise. So in that case, students, my area vector is where? Outside or inside the plane? Where is my area vector?
Outside.
It's going to be outside. Take your fingers, because this is the direction of the current. Of course, curl your fingers around the coil. You'll get the area vector, which is out. But now, since you've got the area vector, students, it's outside. Can you tell me in which direction will the torque be applied? In which direction will the torque be applied? Will it be, how can we find out? So if you know that the area vector is here and magnetic field is inside, then I can say if my magnetic field is basically inside, A cross B, from A to B, so torque will be in the direction of A cross B. Torque will also be,
Sir, upwards.
yeah, torque. Basically, what is going to happen? This thing is going to rotate like this. You understood that? You understood? This is the axis, students. So the entire loop, maybe you can consider this to be the loop. Okay, it will basically rotate like this. It will rotate like this. Why? Area vector of this is coming out towards you. Magnetic field is inside. A cross B is going inside. So A cross B is going inside, students. So my plane also will move like this. A cross B. Is that clear, everyone? Yes or no? So students,
Yes, sir.
this was the end of the lecture for this concept right here. There are various other concepts which we have to do, and various questions which we'll be doing in the next lecture, that is tomorrow morning. There are 2 minutes left. So there are some minutes left. So students, in case you have a doubt, I am right here. you can ask me right now if there was any doubt here, anywhere, any doubt. You can send me a private message right now, or a message. It doesn't matter. Any doubt at all. Yeah. Okay. No one has a doubt. Fine. So students, I'll be closing the lecture right here. If you all have understood this, uh, since there are 2 minutes left, we'll have to go to difficult concepts, and that will take some time. So, yeah. Okay. Let me see. So, will the torque always be in the direction of the current? See, torque is not going to be in the direction of the current. Torque is going to be in the direction of A cross B. Torque is going to be not in the direction of the current. Look here. Again, I'll tell you. Look here. I just told you that if this is going to be my magnetic field, students, if this is going to be my magnetic field like this, and with respect to this magnetic field, I have kept this entire plane of loop here, this loop having some angle theta. Okay, and I consider that the current in this basically is having some direction like this. In that case, if you apply a right hand rule, the area vector is coming outwards. Area vector comes outwards like A, but this is B. And so torque will always be parallel to area vector cross B in this direction, A to B. So area vector, you can see area is like this and B is like this. So of course you can see this angle here. It is going like this, area vector to magnetic. So torque will be moving, this entire loop will move from A to B. It will move like this, from A to B. Okay. Is that understood? You can type a yes or no, or okay. So bye students. The time is up. I will see you in the next lecture. Bye.